Hello dear students, welcome you all. In this lecture, I am going to discuss about the basic properties of atomic nucleus. Basic properties of atomic nucleus. So you know very well that with the success of proton-neutron theory, now it is established that the atomic nucleus contain protons and neutrons, right? Whereas the electrons are revolving around the nucleus. Earlier we have a theory that was known as proton-electron theory, what that was discarded, and the proton-neutron theory that I am discussing here, it is, it is going to be accepted by all because it removes all the objections from the proton-neutron theory, proton-electron theory, right? So now, according to the proton-neutron theory, any atomic nucleus, suppose if this is the atomic nucleus, then it contains protons plus neutrons, that is equal to A, mass number of the atom, whereas the electrons are revolving around the nucleus, right? So that is equal to Z, that is equal to number of either electrons or number of protons, because they are equal, that's why the atom as a whole is neutral. So I am coming to the first property of atomic nucleus, that is the size of atomic nucleus. Atomic nucleus. So we know very well that the Rutherford's alpha ray scattering experiment lead to the discovery of atomic nucleus, right? And we have also tried to find the distance of closest approach in the case of Rutherford alpha ray scattering experiment, that was R naught is equal to ZE square upon pi epsilon naught m u square. U square, it can be b square, that is the velocity of the incoming alpha particle. So this was a rough approximation about the distance of the closest approach from the center of the nucleus, or you can say roughly, if we consider that the nucleus is spherically symmetrical, then this is the radius of the atomic nucleus, and it was found from various experiments that it is of the order of 10 raised to power minus 14 to 10 raised to power minus 15 meter. So this was, the outcome of Rutherford alpha ray scattering experiment. Then after many experiments were performed with different particles, I mean, instead of taking alpha particle as a projectile, we take different particles and then we bombarded these particles on the atomic nucleus, and then we found the distribution of the symmetry of the distribution of the positive charge inside the atom. So from all those experiment, it was found that the positive charge is uniformly distributed inside a spherically symmetrical sphere. I mean, we can say that the nucleus is having a type of spherical shape, right? In the coming lectures we will see that the nucleus is not exactly spherical, but it is having a shape of ellipsoidal, right? So for the time being here, we can say that the nucleus is spherically symmetrical, and it was also found from all those different experiments that the volume of the this nucleus is directly proportional to the mass number A of the atom, right? So different experiments, scattering experiment reveals that the volume of the nucleus, that is spherically symmetrical, is directly proportional to the mass number, right? So I can say, now if I consider that the nucleus is spherically symmetrical, then volume is 4 by 3 pi r cube, directly proportional to A. Here r is the radius of that sphere. So I can say r cube directly proportional to A, or I can say r directly proportional to A power 1 by 3, or I can say R is equal to R naught A power 1 by 3. Here R naught is the constant of proportionality, and by doing various experiments, scattering experiments, it's found that its value varies from 1.2 to 1.6 Fermi. Fermi means 10 raised to power into 10 raised to power minus 15 meter. So this is the relation for finding out the radius of the atomic nucleus of different atoms. R is equal to R naught A power 1 by 3, right? We can say like that. So this is about the size of atomic nucleus. By putting the value of A, I can find out the radius of any atomic nucleus, right? Now I am coming to the a graph. If I plot a graph between the radius and this mass number A, then what I will find? So I am going to plot a graph. This is A, mass number, and this is R, radius, right? So it is found that the graph is of this type, right? You can say this. So we can say that let it is 0, then it is let 20, it is 40, then it is 60, then it is 80, so on. So you can see here that there is very small variation in the size of the nucleus. The radius of nucleus initially increase gradually, and then it becomes almost constant. Clear? So we can also see from this relation, if in A I put 8 here, then I will get, if A is 8, then I will what I will get, R is equal to R naught into A. A means 8 power 1 by 3, so it is 2 R naught, right? If I in place of 8, if I take A is equal to 64, right? Then what I will get, R is equal to R naught into 64 power 1 by 3. So 4 R naught, right? So you can see that there is, as the mass number goes from 8 to 64, right? It is increasing around 4 times, right? But the radius is increasing only 2 times. So you can see, even we can take 125, then I will get 5 R naught, right? So we can see from here that the radius increase very slowly with the increase in the mass number, right? And after attaining your value of around 10 raised to power minus 14 meter, it will nearly become constant, although it will increase according to the fact of this equation, but it will nearly become constant, we can say. So this is the range that is we can say of the atomic nucleus, 10 raised to power minus 14 meter. It can't have a size greater than this. If we have very heavy nuclei like uranium 238, right? And suppose another nuclei that I have is 8 oxygen 16, that is a lighter nuclei. This is heavy nuclei. This is, if I compare the radius of these two nuclei, then there will be only small variation in the radius, right? Radius will not, the size of the nucleus will not be very different in the two cases, right? This is from this relation, right? If otherwise the size of the nucleus is increasing rapidly with the increase in A, then in the heavy nuclei, the size of the nucleus will become very large. And in that situation, the strong nuclear forces, which have a range of the order of 10 raised to power minus 14 to minus 15 meter, they won't be able to handle the such a large size. So the stability of the nucleus will not be possible. So that's why this graph is very important. It says that the radius of the atomic nucleus increases slightly with the increase in mass number, and after attaining a particular value around 10 raised to power minus 14 meter, it becomes nearly constant. And if we want to go beyond that, then the stability of the nucleus is not possible, and the nuclei of all those atoms are unstable, right? They decay mainly through the alpha decay, and then they reduce their size. So we will discuss all these things in the coming lectures, why the alpha decay takes place. So up to till this point, we can say the size of the radius atomic nucleus depends upon this relation, and it has this graph, right? Now I am coming to the next property of atomic nucleus, that is nuclear mass, or we can say mass of atomic nucleus. Now we know very well that according to proton-neutron theory, the nucleus contains protons and neutrons, right? And we also know that the mass of proton is nearly equal to mass of neutron, right? And it is very greater than the mass of electrons. So if we look at the mass of the atom, then about 99.7% of the mass of the atom is present inside the nucleus, whereas the mass of the electrons which are revolving around the nucleus, it is very small, very negligible, right? So the total mass of the atom is the mass of the nucleus, and the mass of the nucleus is the mass of proton multiplied by the number of proton Z plus mass of neutron multiplied by the number of neutron, that is A minus Z. So that will give you the total mass of a nucleus A Z. A is mass number, Z is proton number, or we can say atomic number. So this is the way of calculating the mass of atomic number, atomic nucleus. Now we have seen that this number comes out to be very close to the mass number. When we look at the mass of the different atoms, it is very close to A. In some cases it can be exactly A, but in most of the cases it is either slightly less than A or slightly more than A. So we will see why it is happening in the coming lectures, right? Now, what is the unit that we are going to use for the measurement of atomic mass or nuclear mass, right? So we know the SI unit for the measurement of mass is kilogram, right? But we know kilogram is a very big unit. When we goes to the atomic dimensions, nucleus, then this kilogram unit has no significance. It becomes a very big unit, right? So in that case, we have to invent a different unit that can measure the mass of the nucleus or mass of the atoms. So for that, we have invented a unit that is known as a atomic mass unit, AMU, right? It stands for atomic mass unit. Now this is going to be the unit for the measurement of the mass of atoms and subatomic particles like proton, neutrons, right, electrons. So all those masses will be expressed in atomic mass units. Many times a question is asked that define AMU. So AMU stands for atomic mass unit, right? And it is defined as the 1/12 of the mass of a 1 neutral 6 carbon 12 atom, right? 1/12 of the mass of a 1 6 carbon 12 neutral atom. I am taking carbon 12. It is worthwhile to mention here because carbon has 3 isotopes, 12, 13 and 14. So we are taking the case of 6 carbon 12, right? So now I can calculate this value as we know that the total number of atoms or nuclei in 12 gram of carbon will be equal to how much? N, Avogadro's number. This is Avogadro's hypothesis, right? That all the atoms contain number of atoms or number of species, that is molecules, equal to the either molecular mass or atomic mass of that species, right? We can say whether it is a molecule or it is a atom. In both the cases we will take the in case of atom we will take the atomic mass, in case of molecule we will take the molecular mass. So 12 gram of carbon is equal to n number of atoms, or I can say n is what? Avogadro's number. Its value is 6.023 into 10 raised to power 23 atoms mass is equal to 12 gram. So what is the mass of one atom? One atom mass is equal to 12 divided by 6.023 into 10 raised to power 23 gram, right? Now I can take the 1/12 because 1 AMU is equal to 1/12 of this. So 1/12 multiplied by 12 divided by 6.023 into 10 raised to power 23 gram. So 12 get cancelled. You will get, after simplification, you will get 1.66 into 10 raised to power minus 27 kilogram. So this is the value of 1 AMU, 1 atomic mass unit. Clear? How we calculated it? We calculated it from its definition, right? That we have invented, we have defined. It is equal to 1/12 of the mass of one carbon 12 atom. We know very well, according to Avogadro's hypothesis, this much 12 gram of carbon will contain number of atoms or number of nuclei is equal to n. N is having this value. So we can say that this much of atoms have mass equal to 12 gram. So one atom will have mass is equal to this, then 1/12 is equal to this, and then we got this. So this is 1 AMU is equal to 1.66 into 10 raised to power minus 27 kilogram. Now we can express the mass of proton and neutron in terms of AMU. So mass of proton in terms of AMU is equal to 1.00727, right? AMU unit. Now mass of neutron is equal to 1.00866 AMU, right? So you can say this is the way of writing the mass of subatomic particles like proton, neutron. Even we can write the mass of electron also, right? So you can see here there is a slight difference, right, between the mass of neutron and a proton. Very small difference. We can say they are nearly equal, but the mass of neutron is more than mass of proton, right? So this is the unit for the measurement of mass of the subatomic particles, because there the kilogram is a very large unit, right? Now I am coming to the next property of atomic nucleus, that is energy. In the subatomic world. Subatomic world means energy related to the atomic nucleus, energy related to the neutron, right? energy related to the proton, energy related to the electrons. We know very well again that the SI unit for energy is joule, right? But again, it is a very big unit, right? Large unit. So we can't use this unit because the energy is associated with the subatomic particles is very, very small. So we can, because these particles are very, very small actually. So for that we have to develop or invent a new type of unit, and that unit is known as a electron volt. Right now, just like AMU, that was atomic mass unit. Now I have a electron volt. This is going to be the unit for the measurement of energies in the subatomic world, right? So what is 1 electron volt? 1 electron volt is defined as the amount of energy acquired by an electron when it is accelerated through a potential difference of 1 volt. Suppose I have 2 points, right? It is positive potential, it is negative potential. Suppose I have an electron, right, and I am accelerating this electron from this point toward this point, right, from negative terminal to positive. Obviously the electron will move toward this side. So when, what is the potential difference between these 2 points? 1 volt. So when the electron is accelerated in this potential difference, it will obviously attain some energy, kinetic energy. That energy is called electron volt, and mathematically it should be equal to the multiplication of the charge on the electron Q and the multiplication of 1 volt, right, potential. So it is what? Charge on the electron is 1.6 into 10 raised to power minus 19 coulomb multiplied by 1 volt potential difference, right? So I can say that E is equal to, now because coulomb and volt, this is equal to joule in terms of dimensions. Joule is equal to coulomb volt. They have same dimensions. So I can say energy is equal to 1.6 into 10 raised to power minus 19 electron, joule, right? This energy 1.6 into 10 raised to power minus 19 joule, this is called 1 electron volt of energy, right? Now we can even have bigger units of energy, right? Mega electron volt. Mega electron means, now I am taking the 10 times 6 of this, right? 1 electron volt, 1.6 into 10 raised to power minus 19. So that will become 1.6 into 10 raised to power minus 13 joule. So I will call that as a 1 mega electron volt, bigger unit for the energy. Or I can even write it is equal to 10 raised to power 6 electron volt, right? So this unit, electron volt and mega electron volt, are commonly used in nuclear and particle physics for expressing the energies of subatomic particles like proton, neutron, quarks and all that, right? Now I am interested in finding out the energy equivalent to 1 AMU. Many times this question is asked in the examination, that define 1 AMU, also calculate the energy equivalent to the 1 AMU. 1 AMU means 1 atomic mass unit. So how we can calculate? We can calculate this energy simply by utilizing the Einstein mass energy relation. E is equal to mc square. Now what is the value of m here? M is equal to 1.66 into 10 raised to power minus 27 kilogram. We have calculated it here, right? So I am going to put this value here. So then I will get E is equal to energy equivalent to 1 AMU is equal to 1.66 into 10 raised to power minus 27 multiplied by 3 into 10 raised to power 8 whole term square, mc square. So when I will simplify it, it will obviously become 9 multiplied by 10 raised to power 16. So when I will simplify it, I will get 1.494 into 10 raised to power minus 10 joule, right? Energy. Now I am going to convert this energy in terms of electron volt. So what I will do, I will simply divide this energy by electron volt, right? So it is 1.6 into 10 raised to power minus 19 electron volt. So then after I will get, after simplification, 931.48 into 10 raised to power 6 electron volt, right? This is the expression that I will get. So I can say it as a 931.48 mega electron volt, or commonly we take energy as a 931 mega electron volt. So this is the energy equivalent to 1 AMU, right? So how we calculated it? We simply calculated it by putting the value of M in this energy mass equation, and then we found the energy in terms of joule, units joule, and then I converted this into electron volt by divided it by 1.6 into 10 raised to power minus 19 joule, because we know very well that 1 electron volt is equal to 1.6 into 10 raised to power minus 19 joule. So when I simplify it, I found this value 931.48 into 10 raised to power 6 electron volt. So 10 raised to power 6 electron volt, I can say mega electron volt. So it is 931 mega electron volt, right? So this is about the energy equivalent to 1 AMU, right? So this is all about the some features of atomic nucleus, basic properties of atomic nucleus. In this lecture we discussed about the size of atomic nucleus, right? That was found R is equal to R naught A power 1 by 3. Then I discussed about the mass of the atomic nucleus. Then I discussed about the AMU, atomic mass unit. Then about the energy, right? That is 1 electron volt, mega electron volt, energy equivalent to 1 AMU that we calculated. So this is all about it. Thank you very much.